Good afternoon, everyone, and thank you for attending our How PCB Design Choices Affect Overall Cost from your PCB Fabricator webinar. My name is Ed McMahon, CEO here at Epic, and today I will also be the presenter. Before we get started, I just wanted to let you all know that you'll be muted during the presentation. So if you have any questions as we move along, just go ahead and enter them into the questions panel located at the webinar control panel, and we'll try to get to all of them at the end of the presentation. If we don't have time to get through all of them, we will make sure that we reply back individually to each one of your questions via email. And this recording of this webinar will be posted on our website, and usually we take the questions and we summarize into a blog post as well. So having said that, let's go ahead and jump right in. Today, having a little technical difficulty here. On the agenda, what we decided to do with this webinar is we went back through really over the past 6 months and we looked at a lot of the questions that we were getting from many of our customers, and we went ahead and figured out that, you know what, it would be a really good idea to help everybody understand how some of their design choices add cost and time to the fabrication of printed circuit boards, because there's some things that can be avoided if they are specified in a certain way. So what our objective here today is really to let everyone know how the design choices affect the cost, and then in some of the instances give our customers some options that will allow them to make some better choices that will allow us to move more quicker, along with being able to get some cost out of the overall part. So to start, we're going to just do a couple of definitions, and many of you are well aware of what these terms mean. But really, we're here to talk today about high density printed circuit boards, right? And usually these parts contain blind and or buried vias and micro vias of 6 mils and less in diameter. And technically, if you look at it today, 5 years ago, if you were talking 6 mil lines and spaces, that was really high tech. And now you can get down to 3 mil lines and spaces, and that's really commonplace. So the business has changed dramatically. But along with that, with all of this new technology, it's really required fabricators to invest in a whole new set of equipment. Everything from laser direct imaging to laser drilling to vacuum controlled pressure plugging to different types of de-smear depending upon what the materials are, and different types of equipment has really been required for a lot of these high-density printed circuit boards. Along with, you've heard the term high speed as well, and a lot of this goes hand in hand. The second definition that we really wanted to go through is via types, because we're going to get into a lot of what the different via types require from a fabricator. So when we look at the different via types, everybody is most familiar with the plated through hole to the far left. And that has traditionally been the most common holes that are put in boards. Now you're also looking at what are blind vias, which blind vias mean that they connect an outer layer to an inner layer so they don't go out to the other side. Buried vias are basically, as they say, buried inside of the 2 outer layers, and they can connect any number of different layers. Complex vias, where you're talking about, in this particular case, it's a buried via that has micro vias on top of it. And then the micro vias are what you see there, and in the middle, those are what are called stacked micro vias. So basically, on a micro via side, in many of these buried and blind vias, laser drilling equipment is really required for fabricators to be able to create the type of feature that our customers are looking for. And now with, the finished hole sizes getting, being 6 mils being really common in the designs, this is something that everybody needs to be aware of, because there are certain types of hole sizes, especially micro vias or really small blind and buried, that you can't do with traditional mechanical drilling technologies. You really need to be able to use the laser for many different purposes. So as we look at the IPC definition of a micro via, it's got an aspect ratio of 1 to 1. And typically, these are filled one of 4 ways, right? Typically, if you've got a micro via that is an internal microvia. Many times it can be filled with B-stage or pre-preg. When you do your lamination, the pre-preg heats up and spreads between the traces along with inside of the holes. Or we fill them with conductive or non-conductive material. We can plate them closed with electroplated copper depending upon how small the hole is. And sometimes we'll even fill them with a copper paste. But traditionally, now especially, number 2 and number 3 are becoming the most common way for us to manage microvias and the smaller through-hole vias as well. So one of the things we want to talk about when you talk about vias, and especially with buried and stacked vias, is where do we really add cost, right? And the real reason that we want to look at this is because when you look at something like a buried via, and you look at that over here to the left, you look at that buried via, well, technically what has to happen is that you have to have several different lamination cycles. And the reality is that this is an old flow chart of how to manufacture a printed circuit board. And it doesn't go through every single step, but the whole idea here is to demonstrate what has to happen when you put in a buried or a stacked via. So for every set of buried vias that you have, for the most part, you've got to go through 75% of the processes, right? So once you get out of your resist strip, you have to go all the way back and start over again, because you're going to be basically doing this every time. And that's what adds the cost to the printed circuit board, is because you recognize that you're basically running the board almost 3/4 of the way through, and then you've got to go back and do it again. And along with that, when you're looking at it from a quick turn perspective, I mean, what you don't see in here are any of the bake or pre-bake processes that are required. You don't see some of the other real fine technical processes. But one thing to keep in mind is the fact that certain of these processes take time, and there's no speeding it up, right? There's no, well, lamination, just instead of doing an hour in the press, we'll just turn it up to 2x what it should be, and we'll just do it for 30 minutes. That's not how it works. So with lamination, you're going to spend an hour in the hot press and an hour in the cold press. And when you come into plating, right, it basically takes an hour to get through the entire process in order to meet the IPC specifications, to be able to have the whole wall meet the specifications required by having enough metal actually deposited. So this is what we talk about when you add cost to it, and you wanted to know why. It's because you're having to go back through a whole lot of the processes several times. And we're going to get into more of how each of the individual features kind of stack up here. Because when you look at, this is a traditional 6-layer printed circuit board, right? And when you look at it, this particular board has not only has microvias in it, it's got buried microvias, traditional microvias, blind vias, and a through-hole via. And what this particular board means is, from a 6-layer perspective, is you're talking about 3 lamination cycles, right? So this particular is the first one, where you're taking that material, it's going to have copper on the top and bottom, you're going to drill it, you're going to image it, you're going to plate it. That's number 1. And then you're going to go through and you're going to do it again. You're going to go ahead and laminate copper pre-preg on top of both of those 2 layers. Then you're going to drill those 2 microvias. You're going to go back through the imaging and the plating cycle again. And then you're going to go and do it a 3rd time. And then the 3rd time, you're going to have all 6 layers now laminated together, but you now have to drill that through hole. You're going to drill those microvias that you see here and go from layer 1 to layer 2, and then you've got to go from layer 1 to layer 3 as well. So that's 3 lamination cycles. So that's those processes that we just talked about 3 separate times. Now, when you look at the traditional standard 6-layer, all you would do would be to take, at a traditional standard 6 layers, take 2 pieces of interlayer core with copper on both sides. You would just go ahead and image and etch those, and then you would laminate the whole thing together once, and then you would go ahead and drill your vias and move on. So you can imagine that a 6-layer with blind and buried vias, this is why it takes a lot longer than your standard 6-layer requires. And it's just about physics, right? Those processes that we saw on the last slide, they don't necessarily, you can't skip one, or you can't improve the timing around it. So it is what it is, and it just requires that amount of time to get it completed. Blind versus buried vias, right? This particular, the top one here has got what we'll call three different sets of blind vias, but there's only one lamination cycle. Well, why is that? Well, you've got a specific, these micro vias are on the outer layers so that they can be controlled, that laser drilled, and then you will go ahead and drill the through holes, go through your plating cycle, and you only have to do one lamination cycle. There is one exception, and that is one of those outer layers with a dissimilar laminate, but the reality is that this particular one, because the micro vias were on the outer layers and not on the inner layers, we're able to only do one lamination cycle, which takes a lot of cost and a lot of processing out of the total overall processing. Buried, stacked, or staggered vias all require more lamination cycles. One of the things to keep in mind is a feature that kind of looks like this one here. What you see there is we just talked about the blind vias where you're starting at an outer layer going to an inner layer, and then you're plating through to an inner layer, right? The challenge with these is that in many instances, if you had two sets of blind vias, you would sometimes are able to just basically manufacture two printed circuit boards and then laminate them together. In this particular instance, you can't do that because the blind vias have a common layer. So you can't laminate copper to copper. You actually have to have prepreg in between them. So you would have to basically do this, laminate it, do the blind vias to be able to go ahead and create this function, this feature, if in fact you had two sets of blind vias that terminated on the same inner layer. So that's really why the blind and buried vias add so much additional cost, because you're running through so many different processes. One of the next things we want to talk about is a filled via, and what you see on the right is a conductive filled via. And there's two types. If you're talking about plugging a via with solder mask, that's really simple. That's not hard to do. That's just part of the process of either screening or spraying or whatever you do to coat the solder mask onto the panel before you image the solder mask. So that's not hard at all, right? So really what we're talking about is this conductive or non-conductive epoxy. And as you see from the picture to the right, this is exactly what you want to see from a finished cross-section, right? You've got a very uniform and smooth fill. You've got hole walls that have the correct amount of copper, and you've got a very flat surface on the top. This is how you want your filled vias to look when they're completed. Traditionally, how we would do filled vias back in the day, before all this new technology came out, was using old school methods, right? And when you look on the left, you're talking about a manual screen printer or a semi-automatic screen printer. And what we used to do is we used to go ahead and create an image on that screen where we would then use the via fill, and we would move it across with a squeegee where it would only be administered into the vias that we would want. It's not that high a pressure. There's no vacuum pulling it through the hole. So there was a whole bunch of challenges with that. And this equipment, believe it or not, is still in use today for old school factories who are trying to fill vias with it. The other thing that you'll see is what you see here is the picture right next to this with the blue background is a pumice scrubber, and that's really used to prepare the surface when you're adding something like a solder mask to it. And that's typically sometimes used in old school processes to try to flatten out the process after you put the vias or you fill the vias with any type of conductive or non-conductive paste. Or the one on the right is an old school deburring mechanism, right? Whenever you're coming out of drill, right, and you have deburring from driving the drill bit through the copper, that particular piece of equipment is used to get those burrs off of drill panels. So it's really shouldn't be used in this process, because if you use the screen processing process to try to fill the vias, many instances you end up with a feature that looks like this, right? And as everybody knows who has ever tried to solder a BGA, when you've got vias pads that have via and pad that look like this, it becomes very difficult to make it solderable, right? And you create major challenges. That's not the flat top that you want. And a good portion of the reason that that happens is because that screen is stuck to the actual board that you're screening. And when you pull it off, you inherently will take some material with it. And so that's what creates this particular function if you're doing it the old school way. So there are really three ways to process it. And the reason that I'm pointing out all of these three ways is to let everybody know that there's not one way, but more importantly, to show everybody that every time you do a via fill, it could add 6 to 8 hours. Whether you do it in the process, which is the one on the front where you start by only drilling the holes that need filling, and then going back through filling the holes, and then re-drilling all the other holes, or the process all the way over on the right, which is one of the ones that we use, which is you build a fixture that'll just fill those holes using a mechanical or pneumatic mechanism to make sure either some of them have a vacuum and some of them don't, to make sure that you get full coverage inside of that vias to reduce voids. One of the big reasons why this takes so long is because regardless of the mechanism that you use, you have to bake the panels themselves for 2 hours before and an hour to an hour and a half after to make sure that A, the panel is prepared to accept the material that's going in, and B, afterwards to make sure it's fully cured. And again, just like going back to a cooking reference, right? You can't just say, well, just push it up to 300 and you'll get it only do it for an hour, okay? There's a reason that it's in there for 2 hours, and that's because we have to have it uniform all the way through. Otherwise, you're going to have voids inside of those vias, and that's going to be a challenge. And again, this is what the equipment looks like when you're creating proper filled vias, right? You've got two different types. One's a vacuum assisted and one isn't. That's filling the vias. That piece of equipment in the middle is what's called a planarizer. And really, if you're forcing pneumatically through the panel and after cure, you are going to have some run out onto the flat surface of the panel. So you need something that's going to take a little bit off of the entire panel, but make sure that you have a flat and uniform surface to get to that over on the right, which is a flat surface that you can solder on. It's wildly important that you have these proper pieces of equipment in place to do this correctly. And just so that everybody understands, from greater than 10 mils to 18 mils, it's really easy to fill, right? The hole is big enough. It's just, you can absolutely do it, above certain sizes, it just doesn't make sense. But 10 mils and above, it's pretty easy. Less than 10 mils, it may be easier to plate shut. Depending upon, 8 to 10, it gets a little hairy. 6, it's really tough. Because just the physics of it, because the process is you drill the hole and then you plate it, right? Remember that if you're looking for 1 ounce of copper inside of your plated through hole, that's 1.4 mils on each side, right? So, you're talking about almost 3 mils you're taking out of that hole. So the smaller we make the hole that we're trying to push this thing through, the harder it becomes. Frankly, for us in our factories, both in the U.S. and in Asia, if it's 8 mils or less, we automatically just plate it shut. It takes a little bit longer in plating, but over time, it's a much more reliable connection and reliable filled vias. But this is why filled vias take so much additional time, even though many folks don't recognize why that is. The next thing we want to talk about is castellated edges or half-plated holes, because this has been something that has become much more common. And as you can see behind this thing over here on the right, you're seeing this is a 27-ounce copper board that we make that's got some half-plated holes. But that's not what we're here to talk about. We're more here to talk about things like this, right? When you look at what you use a castellated or half-plated hole for, it's a mechanism to attach a printed circuit board to another printed circuit board without a connector, right? So what you're seeing on that below is, a printed circuit board that's been populated, that's some sort of unit that we're going to place onto another printed circuit board to be connected to something else. everybody kind of has their secret sauce around how they create this particular feature. But it's really important to make sure a customer specifies what is acceptable, because while it seems like it shouldn't be that difficult, it really is pretty difficult to get the features the way a customer wants. Everybody has seen something like this if you've worked with these half-plated holes. And traditionally everybody thinks, oh, it's a half-plated hole, so what do? I just go ahead and I put plated through holes all throughout the outside of this board, and then I just run a standard router bit through the whole thing. And then what you get are what you're seeing in this particular picture, and that is you're seeing all of that copper that came off of the other side of the hole. And you say, well, it shouldn't be a problem because it only came off of the other side of the hole. So many shops just take a good old-fashioned hard wire brush and just wire brush all of those off of each one of those holes. And it creates huge problems because when you do that, you're loosening the copper plating from the hole itself. And so while it may look like it is there and it is absolutely not going to be a problem, a lot of times during soldering, you'll find that those little slivers will come off, and then you'll find them attaching themselves to other features on this module and what it is and creating shorts. So it's really important that as a customer, you identify what is acceptable to you so you don't get this. And we've even seen many fabricators try to even score through many of these types of boards and create more of a problem. The one thing that many customers don't recognize is if you try to use this method, right, and you want to run the router bit around the outside of this board, the bigger problem is that right here is where, to the right of this little, of the center of this is where the router bit plunged in the first time. So as you're going around this rectangle, everything is great because from a dimensional standpoint, because you still have enough of this little piece attached to the base laminate itself that it's not going to move. But at the very end, when there's nothing else, and if you use an 031 or an 062 router bit or whatever it is, right as you're about to finish this part, that part will move. And you will have some sort of a knob or a hump or something like that will traditionally take this out of alignment. Now, in order to fix that, there's a couple ways to do it. And what ends up happening is that many fabricators will come up with some sort of a tool. And that is because they'll take pins and they'll say, okay, we're going to set this on top of, we're going to use those plated through holes and put them down on pins. And all that really does is create significant damage inside of those plated through holes. So the real key is to have some non-plated through holes in here, or to use double-sided tape, which creates its own challenges. But at the end of the day, this creates challenges because 9 times out of 10, a customer is going to get what they don't want. And then when they identify what it is that they want, and the fabricator realizes what steps are going to be required to get it, it creates more cost for the customer. The next one I want to talk about is cavities, air pockets, and heat sinks, because these are ones that we are now starting to see an awful lot of, especially in the RF world. And it creates some challenges and that we want to talk about to help our customers do a little bit better here. Cavities and air pockets, right? I mean, this is becoming more and more commonplace all throughout the printed circuit board world. When you look at it, right, usually these cavities and air pockets require some tight tolerance machining, whether it's a controlled depth, whether it's you know the type of tolerances that go along with machining, like down to a thou, right? And many of them also require, in certain instances, that we use a no-flow pre-preg because we have to actually do a couple of lamination cycles, and that also requires intricate machining. So how can customers help us? Well, number one, the one thing you got to remember is that traditional printed circuit board CNC equipment is really not suitable for tight tolerance machining. So what do we mean by that? Right, well, first of all, when you look at these two on the top, you're going to see 90-degree edges on internal features. And with traditional printed circuit board CNC equipment, it's very difficult, if not impossible, to get to those 90-degree features. So what is easier for us and what is more cost effective for you as a customer is to do what we do down here in the bottom and allow radiuses, right? And what that allows us to do is use our printed circuit board manufacturing equipment to create those features. That is much more cost effective than having to actually machine those 90-degree edges. Now again, can it be done? Sure. You know, we're fortunate that we own a machine shop, but not everybody does. So that has to go out to be machined when you're looking for those 90-degree corners. So if you can work with your fabricator to look at those radiuses, we're going to be able to move quicker and we're going to be able to keep the cost down. Sure, does that mean that the opening may have to be slightly larger to accommodate the component that you're trying to put down there? Possibly, but hopefully that hole, you'll have enough space to make it so that that hole will still not create a problem for you when you're doing assembly. Heat sinks. You know, heat sinks are usually made separate. They are everything from, you know, these two aluminum ones, but they're also anodized, and they require a lamination press, right? Typically, in these type of applications, we're not taking, you know, you'll see it in the membrane switch business where you take a 3M adhesive and you just put it underneath this and you route the whole thing out and now you just peel and stick. Well, that's not what these heat sinks require. We actually have to attach these using no-flow prepreg. And the way that you do that is after you get the heat sink, you create basically a copy of that that's a little bit smaller that goes underneath this into a tool that you build that goes into your lamination press. And for anybody who doesn't know what prepreg looks like, if you grab a piece of paper that you take out of your copy machine and you grab it and flop it around, that's what prepreg feels like. So when you have to cut a piece of prepreg that looks like that top heat sink, it becomes very difficult and time sensitive and timely to do, right? It takes a long time. And along with that, you have to make sure that you have the right type of prepreg, because it may be the right type of prepreg to flow for the printed circuit board, but remember that you're utilizing a heat sink. So you may have to get it to a temperature that's going to get that piece of metal high enough where the prepreg may not work. So that's why it's really important to get with your fabricator and talk through what you're trying to accomplish so that we can make sure that we're helping you, because if not, it becomes really difficult. And now you're talking about, okay, we're building an FR4, but we got to use a PTFE or a polyamide prepreg because this piece of aluminum is going to suck all the heat away from the prepreg and we can't get good flow. So it's beneficial to work with your fabricator to make sure that you've specified the right material when you're looking at heat sinks. So now we're going to talk a little bit about hybrid PCBs. Excuse me. The definition of hybrid PCBs are things that have two different materials in the same stack-up. And it's pretty common now, especially in the RF world, when in an RF application, if there's a communication portion of it, to be able to put that portion on one end of the stack-up, very similar to the top one here, in order to only have one printed circuit board. That's pretty common. It's relatively easy to do. So what's the challenge with this particular thing that many of our customers don't recognize? Well, the biggest thing that we end up dealing with is the stack up, because as you see over here on the right, the way that we're stacking up the FR4 portion of it doesn't exactly equate to the same way we're going to stack up the PTFE or the antenna portion of the stack up. In many instances it will, but in some instances it won't, right? In this particular case, we're using 2 plies at 1080 when we're looking at the FR4 part, and then to get the Rogers part, we need to use a 2116 and a 106. So the real help for us is when you're looking at designing a hybrid PCB and you're looking at making sure that you're getting all of the RF requirements that you need, is to get your fabricator involved early. Because what we see a lot of is our customers will make the assumption they can just stack it up the way they're doing the FR4, and then we go into manufacturing, we tell them that you can't because you're not going to get the adhesion you required, so we got to stack it up using this, and now that throws off many of the RF characteristics that they were hoping for, so now they have to go back and change much more, and it causes delays. So for us, we like to work with our customers from the very beginning. They give us the stack up they're trying to do. We give them what the most cost-effective stack up would look like, and then they can go through and build off the rest of their part. Because again, and it also is about cost, right? I mean, there's probably 10 different ways to stack this up, and it's all around what do I have in-house, what's the most common pre-preg, and as a manufacturer, I can help you with that. I can't help you identify what you need for your application, but I can certainly help you get cost out of this design by telling you what's the most common and most cost-effective ways to help stack it up. Talking about materials, because we, over the past couple of years with lithium batteries becoming a big part of our world and with in solar panels, we've had some challenges here. So, materials are, a big thing for lead time and cost especially, right? And one of the things you find is that, especially in the U.S., all the manufacturers, we usually have one major supplier and then several minor suppliers because we don't have enough business to go around to everybody. So the whole idea is that, someone who is strong in Isola isn't necessarily stocking Shenyi, right? So the whole idea is that you want to work with your fabricator to make sure that you're specifying a product that they have in-house, especially in the U.S. for quick turns. If you're talking about Asia, the same goes for that, except you don't want to limit yourself to the fabricator. If they're buying 100,000 square feet of one laminate a month, then you want to help them leverage that to get you a better overall cost. So by you going to them and saying, what are the best laminates that you have the best economics on, you're going to help yourself when you're looking at the overall cost, especially in high volume applications. The other thing that we see is copper weight. We happen to be very prevalent in heavy copper printed circuit boards. So because we have a huge supply chain. We negotiate with the manufacturers both here and in Asia every year for 4-ounce interlayer copper cores, because we know that our 8 biggest customers are going to use so much of it, and because we know that a lot of these manufacturers don't like making the heavy copper cores. It's not wildly profitable for them, so you have to be able to negotiate that up front. So you want to make sure that you're working with somebody who's got that, because if you have somebody who's going to order it and then they have a problem and they have to scrap it out and they got to go back and only get a little bit of it, it could be a while before they get it, right? So copper weight is another big portion of it. And the last part on materials is the weave type. That's become a bigger and bigger portion of what customers like to spec out. And the reason is because a lot of the values of the laminate change depending upon the weave type, right? So if you're working, and if your application is so critical that you're getting down to the weave type of the laminate, you really need to work with your fabricator to make sure that that's accessible when you need it, and that from a cost perspective, you give your manufacturers enough time to be able to procure that. I mean, as many of you know right now, trying to get DuPont laminate on the flex side right now can be 14 to 15 weeks. So being able to work with your fabricator ahead of time is really critical if you're trying to specify a certain product by vendor name rather than by anything else. And that's really the biggest thing on this next slide is the 4101 data sheet on IPC. One of the things that you see is when you go back to this, customer says, oh, okay, I want this iTech IT 185 product, okay? But what that does is that limits your fabricator to that specific material. And in many applications, it's required, right? We see that a lot with things like Rogers and even Arlon and even some of the Megtron product, where you can't deviate because it doesn't have the properties required. So we get that. But 90% of what we see doesn't have that. So the whole idea of this IPC 4104, and it's sometimes referred to as the slash sheet, is it gives our fabricators flexibility, right? If you're looking at FR4, and this is really just if you look at the /21, which is the top one, and you went into the IPC 4104 spec, it's more than just this. But this is just kind of the summary sheet. And it shows that for FR4, here's what a couple of them look like, and there's several more. One below it is one of the polyamide ones. So if you specify a IPC 4101/21 as the material that you want, when the material manufacturers, all of these folks are putting that slash number on their data sheets. So you can go to the data sheet and you can look, and many products will fit more than one slash number. But what this does is it creates flexibility from a cost perspective, because I'm going to have material that meets the same specs, but it may not be by that exact laminate manufacturer. And in many instances, it's not that required to have that. So that's why this IPC 4101 slash sheet, using that to outline what you want for material, gives your fabricator flexibility from a cost and from a delivery perspective. The one last thing I want to talk about is AS9100 inspection. With the aerospace and military folks, we do an awful lot of this. And the reason that we want to talk about it is to really let everybody understand why it takes so long, right? An AS9100 inspection requires a bubble drawing. And on printed circuit boards, in many of the cases, our inspection paperwork outside of that really already has that particular information there. But it's not just the bubble drawing that's required, but technically a lot of times it's required to have inspection software, right? We happen to have, a CMM that we invest in that helps us do all these measurements. But when you look at it and you're going through and you're looking at all of the notes and having to go through each one of them per board, it really becomes overkill, and it can take up to 4 or 5 hours. This board on the right happens to be a very simple part. And the problem becomes is that if you look at the more complex it becomes, that has potentially thousands of features, it takes an awful long time to do it. Now, we understand that for production parts, it's absolutely required, and we're very capable of doing it, and a lot of fabricators can, but it's just understanding what is actually what it entails, because it's not as simple as, just going ahead and doing an inspection report. So, a few more things to know. One, when you're talking about Teflon materials, why does it cost so much? Well, we all know that the Teflon materials are wildly expensive. But at the same time, your drill hit count's reduced by 50%. You got to slow your speeds down on many things, on many of these processes. So just your drilling time could go up by a factor of 2. So that's an additional cost in Teflon. With PTFE material, one of the things when you're doing high volume processes is that this material, in many instances, the second you take the copper off, it will change in 2 directions. So the longer you let it sit without going in the press, the more chance you have of the material's registration changing. So that's why typically with us, when we manufacture, we don't etch unless we're going right into the press within an hour, because we want to make sure that we do that before any of that contraction hits. AnyPig, we've been talking a lot about this. Most fabricators outsource this. There's a couple reasons. One is because it's very expensive, not as an actual finish itself, but just as trying to get the bath in your process. And without enough use, it'll plate out really quickly. So a lot of folks fabricate this. At our factory here in the U.S. and Asia, we have it in-house. But if you don't, you got to outsource it. And there aren't that many people that do it. One of the most popular is in California, so you add a lot of time as you're having to ship it from one coast to another. And then lastly, embedded resistors have become a much bigger part of our business. And what we're seeing is that there's some misconceptions about tolerance. And honestly, bigger is better for tolerance, right? If you're looking at taking a 25 ohm resistor, a 25 ohm material with a plus or minus 1 etch tolerance, right, which is what we usually use, is a plus or minus 1 etch tolerance. The larger you make the pad size, the better chance we have of staying really close to what you're trying to get with that 25 ohms. But if you look at this example, right? You basically look at the 10 mil by 10 mil. If we're on the low end of the tolerance on one side and the high end of the tolerance on the other, which means that the pad is now 9 by 11 instead of 10 by 10, you're only going to get 20 ohms. Versus if you got 100 mil by 100 mil and we get the same thing, all of a sudden you're pretty close to what you wanted. So we just point this out because it's really kind of a newer technology, and if you're trying to get in better resistors, like I said, the larger the better for yield perspective, because each one of those resistors gets tested at electrical tests. So from a yield perspective, the bigger you can make the pad, the better it is for us from a cost perspective, because we're not going to have to factor in so much yield. So really in summary, design choices factor into the cost of and delivery of printed circuit boards. It's one of those things that we talk about all the time with customers. You can have anything you want. It's hard to give you everything, right? And so that's why, we want you to call us early so we can help you with that process. Not all vias are the same, and we've talked about that ad nauseum here, but, there's a lot of difference between how many times parts have to go through processing depending upon what they have as via. Material choices, right? We go back to this again, that there's lots of choices out there, but there's also ways you can help yourself, especially when it comes to cost and delivery. And when delivery is paramount, you can make it easier on yourselves and on us. And we're there. Every fabricator is there early. And I don't care who your fabricator is, every one of them, if you ask them, would much rather be brought in early. We know that you say, well, we're not getting paid for that. So what? That's what we're here for. That's why we all do free DFM, right? We want to be involved early so we can make sure that we give you the best service that you're looking for at the very end. All right. My team's going to review the questions that came in here. Holy smokes, there's been a bunch of them. But I wanted to briefly mention a couple things. One is we've got some additional upcoming webinars. This is, I think, somewhere in the 15 or 16 that we've done over the past couple of years. So we've got these coming up. We have another one coming up in August on printed circuit boards. We were supposed to do this one at that time. We decided to change it due to the fact that everybody was kind of stuck at home or stuck sheltering in place, so we wanted to do it now. But we have a couple more webinars coming up. Along with that, just the history of what we offer for products. As we talked about today, printed circuit boards, but our expertise goes far beyond that. And, again, from our perspective, everything started with a printed circuit board over 65 years ago here outside of Boston. So from a questions perspective, I'm going to take a couple of them here. The first one is, what are the biggest cost adders when you go from a Class 2 to a Class 3 or mil-aero type specification? That's a really good question. And as a fabricator, there's really two big things that are required of us that are different. The first one is there's an annular ring specification that's required. For Class 2, both internal and external, it's called there's a 90-degree breakout. So if you have a drill bit or a hole where the drill broke out of the actual pad, that's still acceptable from a Class 2 perspective. However, in Class 3, what that requires is on an outer layer, you have to have a minimum of 2 mil annular ring, and for an inner layer, a minimum of 1 mil. So that creates some challenges on several different fronts from a cost perspective. One is you got to increase the pad sizes by almost 40% in some instances. So you're really spending a lot of time going through on the cam side, making sure that you've got all those pads blown up there, and that you can still make all your required clearances through the rest of the features. The second thing is that typically when we do drilling in printed circuit board manufacturing, we like to stack product up in the drill. So you'll stack four boards up and you'll drill all four at once without changing it out. Well, typically there's a couple things. One's called drill wander. So you really on Class 3 boards have to be careful, and many times you don't stack it up because you don't want the drill wander to create breakout. Along with you've got to slow it down because there's this feature called rapid runout. If the drill bit isn't sharp enough and the bit hits the actual copper itself and then begins to shoot to one of the directions and outside. So it really cost us a little bit more to produce. And the second thing on class 3 is plating thickness. For class 2, you got 0.8 mils in the hole minimum. For a class 3, it's 1 mil in the hole minimum. And as you know, if you put a mil in the hole, you're going to have, or if you put an ounce of copper in a hole, you're going to have about 1.3 to 1.4 mils. Now, the real issue with this is that the way you measure this on a class 3 or on a mill board is on the coupon, right? You're not going through and measuring every board to see if you have that amount of copper. And the problem is that the coupons are on the edges, right? So you want to make sure that those coupons come out good, because if the coupons come out good, the theory is the rest of the boards will come out fine. The challenge becomes that if the coupon's bad, basically the panel's bad. You can't say that, oh, the boards inside the panel are fine, just the coupon's fine. So that's why it takes longer, because we have to make sure that the coupons are good as well. So that's what adds some cost to class 3 versus class 2. Another question here is, how does tight lines and spaces affect the cost of manufacturing? Another good question. In all honesty, it really doesn't. You know, whether you got 3 mil lines and spaces or 6 mil lines and spaces, it doesn't necessarily matter to us. What it does is it matters what kind of equipment you can use to do it, right? The traditional photo imaging equipment is really difficult when you get anywhere below 6 mils. So you really need laser direct imaging. So really, when you're going down to that level, you've got to have the proper equipment. So you're more just limiting the number of people that can do it. The other thing to think about when you're talking about that tight lines and spaces, and the biggest challenge that we normally have is, 4 mil and under solder mask dams. That's the biggest one that we find that we have trouble with. When you have a tape test and you didn't process that with an LDI, and many companies only have, don't use LDI for solder mask. Well, if you don't use LDI and you don't go through the right bake cycles, it's going to be really easy to pull those 4 mil dams up on a tape test. So that's the bigger thing with tight lines and spaces, is that kind of stuff versus any real cost adders. Another one is, how does material yield on an 18 by 24 panel affect the cost? It's interesting, for the last, 20 years, 18 by 24 was the panel size that everybody used, right? And that was just what we used as an industry, and that, did well when you were talking about how it came out of the panels that we got it from. But when you looked at post-etch punch and X-ray registration, that was really good to help us stay with 18 by 24 panels as the tolerances got tighter. But in all honesty, when you get down to where we are today with some of these features, an 18 by 24 panel is really just too big in many instances. So we go ahead and we shrink it down, and in many instances, even on some of the Rogers material, even a 12 by 18 is too much to be able to manage. So a lot of fabricators basically get the material in a 48 by 48 inch sheet. And domestically, when we're doing it, because we're usually dealing in smaller panel sizes, it's even better if we have to manage a larger amount of smaller panels, because you're still not talking about that many. And the thing in Asia is that because there's so much automation, the fact of the matter is that the handling isn't a big issue to them anymore. So even though they're using smaller panels and they're getting a better yield out of the 48 by 48 inch sheet, that's more important these days than what you can get on an 18 by 24 inch panel. So it used to be 18 by 24 was the holy grail. It's not really so much anymore, especially as the technology gets up. One more question here. Do the same cost adders apply to rigid flex? Yes, they do. And for all the features that we talked about here, all of those features for the most part are available on rigid flex parts. But there's some additional ones when we do rigid flex, right? The number one rigid flex challenge you have is the construction, right? And the stack up is probably the biggest challenge that we have with customers. And the one big misconception about rigid flex is that, you just make a rigid board and then you stack it up in through the rest of a flex board, and then you stack it up in the rest of the rigid board and that's it. Well, that's technically not how it's done. the way that it works is that the cover lay portion of that flex circuit doesn't go all the way through the rigid parts of the board. So that's where many times if a customer is looking for something quickly and sends us into design that has the cover lay going all the way through, that can cause us to slow down a little bit as we go through and do a redesign, because now your stack up, your overall thicknesses can change and we need to be addressed. So that's one of the biggest things we see. And then the last thing that we see on that is really understanding with the customer what the bend radius is, because the thinner the material, the more expensive it is to process, right? It's just the way that it is. So if you're not bending this that much, well, you can actually get away with some thicker material and some thicker copper, which is actually easier to process, right? If the thinner the material, if you try to take a 2 mil or a 1 mil piece of polyamide and run it without a leader through old rigid processing equipment, you're going to wrap that around a roller, right? So that's why it's important that if we understand what the application is, we can help you create the most cost-effective solution from a processing perspective. So that's why, on rigid flex, there's a whole lot more. We can do a whole Q&A session about that, but there is some additional things on the flex and rigid flex side. So I just wanted to say thank you. Hopefully this was informative, and we will be sure to post this on our website shortly. And for those of you whose questions I didn't get to, and there was quite a few, we will reach back out to you individually with an answer to your question, along with putting together a blog post with all of the questions answered. So thank you again, and we hope to see you on another one of our webinars.